Hi, everyone. Welcome. I'll give one more minute for folks to come in, and then we will start probably a minute past the hour. Thanks for joining us today. Okay, looks like we're ready to get started. Everybody, welcome to our end of summer BDC Presents. We are so grateful you're joining us today, and we hope you have stayed cool this summer, which is one of the topics of conversation today. I am Jess Silberburn. I am the Thermal Energy Network's Communications Manager at the Building Decarbonization Coalition. And today we will share findings from our new brief, Building Decarbonization Meets Water Conservation, the potential of thermal energy networks to cool buildings and save water. And we will also hear from the person who has personally seen that potential at his facility, Colorado Mesa University, which is the beautiful campus in Western Colorado that you are seeing here. Next slide, please. If this is your first time here, welcome. Happy to have you. This webinar is part of our series BDC Presents, in which we spotlight issues, trends, news in building decarbonization and electrification. And if you are new to us completely, the BDC, the Building Decarbonization Coalition, harnesses the power of coalition to transform the nation's buildings through clean energy. Our coalition members include utilities, nonprofits, environmental justice organizations, research institutions, policy experts, manufacturers, all of whom want to see buildings and communities more resilient to the impacts of climate change. If that sounds good to you or sounds like an interest of yours, you want to learn about our membership, it's free. Please visit our website, which is buildingdecarb.org. And you can also sign up for our newsletter there to hear about more upcoming events. Next slide, please. I want to give a special thank you to our Trailblazer members. These members do help make this work possible through annual donations and financial support. And that is, what helps us keep all of our webinars like this one free. All of our reports, all of our resources live online. They're free and accessible to everyone. So thank you to these members. Next slide, please. Okay, we have a very busy fall coming up, so hopefully we will see each other again. In September, the BDC is co-hosting a panel discussion with the Interfaith Center on Corporate Responsibility in New York for New York Climate Week, which is very exciting. This is actually also going to cover thermal energy networks, so some overlap with what we're talking about today, but it's going to be from the perspective of investment during the energy transition. And then back online a couple of days later, a brilliant panel of speakers is going to discuss the future of gas as a conceptual and regulatory framework. And this is actually a special 1.5-hour BDC Presents presentation, and it's not one you're going to want to miss. And then in October, we are going to host a policy call with our New York team. And the team is going to catch us all up on New York's incredible policy progress and what is next on the agenda for building decarbonization in the Empire State. Next slide, please. Okay, so you have probably attended a few webinars by now and might know some of this, but just for the record, everyone is muted. If you're not muted, just take a look in the corner. Please mute yourself. But please use the chat. We like to have a lively chat during these presentations. So if you have any questions, comments, please feel free to drop it in the chat. My colleagues, Tiffany is here. We'll keep track of all of the comments in the chat and we will answer as many questions as we can. Any questions that we can't get to, we'll answer in a document that will be sent to all attendees next week. Also, if you missed something, taking notes or have to step away, don't worry. This webinar is being recorded and it will live online in our website's resource library. And then again, everyone here will be emailed a link with additional resources, questions early next week. Next slide, please. Okay, with that, it is my pleasure to introduce our speakers for the next hour. Ashley Besic is the Senior Associate for Thermal Energy Networks at the BDC. She convenes multiple stakeholders to develop a comprehensive strategy for a phased managed transition toward clean energy. Ashley organizes proceedings for the BDC's National Thermal Energy Network Coalition. She oversees equity initiatives for our team. Before joining the BDC, she implemented the Urban Land Institute's net zero imperative, and she established sustainability initiatives at LiveCorp. Ashley holds a Master of Science in Real Estate, a BA in Multidisciplinary Studies, and certifications as a lead Green Associate, a Fitwel Ambassador, and Green Globe's Emerging Professional. On top of all that, she is also the author of Building Decarbonization Meets Water Conservation, so she'll be talking about her work on that brief today. Then we have Kent Marsh. Kent, thank you for joining us today. Kent is Vice President for Capital Planning, Sustainability, and Campus Operations at Colorado Mesa University. His breadth of work includes operations management, business management, construction management, building and grounds maintenance, sustainability, higher education planning and funding, and engineering. And Kent holds an MBA from Colorado Mesa University. And I am Jess Silber-Byrne. I am the Communications Manager for Thermal Energy Networks, and I will now yield the floor to my colleague, Ashley. Ashley, take it away.
Great. Thanks so much, Jess. And thank you all for attending. Today, we're talking about our new water brief. As Jess said, it's Building Decarbonization Meets Water Conservation. It's a 10-page survey and analysis of existing data that supports the potential of thermal energy networks, or TENS, to cool buildings and save water. We'll go through our key findings, and we'll discuss why now is an important time for us to collect data from even larger sample sizes than we did for this report. And then we'll hear from Kent Marsh at Colorado Mesa to learn more about their thermal energy network. Next slide. The United States is dealing with multiple climate-related challenges, as we all know. And so some of us may have seen or heard some of these headlines. When it pertains to heat waves, we've heard that data from about 50 US cities show that the heat wave season is now about 46 days longer than it was in 1960, and the occurrences have tripled since then as well. We know that our buildings are thirstier because the heat waves make cooling buildings a necessity, and the proliferation of data centers means even more buildings are trying to stay cool. And finally, we all have heard to some degree that the current estimate of people living in the US in drought-prone areas is close to 40 million. But what we may not have known is that cooling large commercial buildings to safe, comfortable temperatures is associated with all of these challenges. Next slide. So what actually makes a commercial building thirsty? Well, many of the commercial buildings use a combination of chillers and cooling towers. Chillers use refrigerant to absorb heat, and then the cooling tower comes in to consume, evaporate, and discharge that water to release the heat, which means that just simply by working perfectly, the cooling towers are designed to consume tons of water. An estimated 5 to 15 billion gallons of fresh water are consumed daily for cooling commercial spaces in the US, which is a lot of water. What's more is that the water needs to be chemically treated to prevent pathogens. So just by using those cooling towers, you're adding an additional operating costs and risk associated to cooling buildings. Next slide. Evaporating cooling towers have already become a target for water conservation in arid areas. Let's talk about Los Angeles. This picture you see highlights the prevalence of cooling towers on top of buildings in downtown LA. Across the entire Los Angeles County, these systems were estimated to consume over 2.5 billion gallons of water annually. That amount alone could supply approximately 15,000 homes with water. So when in 2018, Southern California was experiencing water scarcity, the mayor of Los Angeles encouraged building owners to upgrade their cooling towers as a way to save water. A more recent example came in 2023, when the Southern Nevada Water Authority Board of Directors voted to support a moratorium on installing evaporative cooling towers in new buildings in the Las Vegas Valley. Next slide. And so we wanted to take a closer look. We love thermal energy networks, and we knew there was a potential solution to the issue by using TENS, because several sites were already reporting those significant water savings. And so our investigation proved fruitful, and that is why we wrote this paper and why I'm sharing it with you now. If this is your first time learning about thermal energy networks or TENS, welcome. We're glad to have you. TENS is an umbrella term for neighborhood scale systems that use a network of underground water-filled pipes for heat exchange between buildings and energy sources. Let's think homes as the homes and data center as our energy sources, and then the water pipes are that using that to exchange. And it's very similar to how the stable and mild temperature of our Earth works beneath our feet. Kent will give a better example and better detail on exactly what thermal energy networks are. But the important thing to note is that the TENS do not use evaporative cooling. Instead, they're actually using ground source heat pumps in every building to move that thermal energy through the network of underground pipes. That heat pumps acts as a gatekeeper and prevents and accepts heat from moving that thermal energy through a compressor, which is similar to a refrigerator. Trust me, Kent will get all into the engineering details. That thermal energy is then picked up by the network and can be moved across and through buildings, or it can be stored in a thermal reservoir. Think of a borehole in the earth. Next slide. Thankfully, TENS already exist across the country on campuses, at airports, and neighborhoods, and communities. They are usually installed to decarbonize and electrify. They connect multiple buildings so that they can decarbonize at neighborhood scale. TENS use, oops, I apologize. TENS use ground source heat pumps, which are extremely efficient. They don't use combustion, so they instantly reduce carbon emissions and as well remove on-site pollutants, which improve air quality. These are all great benefits, but we think, like I said, we're biased, that thermal energy networks are overachievers. So we wanted to survey and analyze their water use and savings too. Engineers already knew that TENS save water compared to cooling towers. It makes sense, right? Because the heat pumps are saving water because they're moving heat from place to place as opposed to trapping that water and evaporating it. But we still wanted to see what was available when it comes to the data. And so, next slide. Here's what we did. We reviewed publicly available data from 10 thermal energy networks, 9 in the US and 1 in Canada. Then these TENS were analyzed, and we looked to find that they were a combination of college campuses, business campuses, and an airport. That data included self-reported information on both water savings as well as energy reduction and energy savings. We standardized it in a table and asked people with experience designing these systems to review this information to confirm the water saving numbers. Next slide. We found that there's plenty of data available to confirm that TENS not only save water, but they save a lot of water, okay? In fact, between the 8 sites that shared their savings in terms of gallons, we found that they saved 337 million gallons of water annually. That's the equivalent of annual use of 3,000 US households. Or if you just finished watching the Paris Olympics, that's about 511 Olympic-sized pools. Next slide. We also found that the water savings were variable. Because this was a small sample size, the annual water savings ranged from 18 to 46%, or 3,000 to 18,000 gallons of water per cooling or heating ton. This raises questions that we hope will help to optimize the design of TENS for future water savings. Future data collection should explore exactly how these savings are achieved by asking the following questions and more. What was the site's total water consumption for heating and cooling before installing a TEN in a geothermal system? Do these institutions distinguish between water used for cooling and other purposes such as sanitation, irrigation, or drinking? Did they retain any cooling towers or eliminate them completely? And I think it's important to note here that we found that tracking water across the country varies so drastically. And so having some type of standardization to both track and measure water performance is just as important as what we're doing in the carbon space. Next slide. Finally, we were very excited to see that the diverse geographic and climatic success span the entire North America. And so although specific areas of North America are experiencing prolonged drought, water scarcity, and overconsumption can be a problem anywhere, these sites show that water savings across climates, altitude, and in differences in average humidity and precipitation. With that, I will stop talking and I will hand it over to Kent Marsh, who's calling from mountainous and semi-arid Grand Junction, Colorado. Take it away, Kent.
Ashley, thank you. And thanks everyone for joining me today. I want to thank Jess for inviting me to be part of the presentation. My role this morning is to do my very best to describe a thermal energy network. My slide is, it's kind of broken down into three different parts. The first part is describing what makes up our system, and I'm going to do my best to describe. There's 4 or 5 parts and pieces to the system that define the majority of what we do here and what our tin is made up of. And then I'm going to try to describe how we can move heat from either just within a space within a building and move it to another space, or to pull heat and move heat amongst various buildings on campus. And then I'll talk briefly about why we did this, why we made this decision back in 2007. Next slide, please. So each of these things that I'm going to talk about, I'm going to try to describe in greater detail. But from the big picture, our tin is comprised of miles of high-density polyethylene piping. The diameter of that piping is as small as 1.25 inches, and those are the pipes that we drill down into the earth and that we use to exchange heat between the ground and our central loop. And those pipes vary in size from 8-inch diameter up to 18-inch diameter. So the large pipe that moves energy from the south end of our campus to the north end of our campus is actually 18 inches in diameter. We have a little over 2.5 miles of that central loop pipe on campus. Our campus is about 144 acres. We had 8 separate drill fields, but we just drilled a brand new one this summer, so we actually have 9. We had 427 boreholes, but I added 60 more, so we're just under 500. And this summer, we were actually able to dig those holes down to 600 feet. Technology has improved, and so we got another 100 feet out of each one of those holes. This is kind of a scary number, but once you're around heat pumps and you understand how they operate, it's not so bad. But we have 1,000 or more heat pumps that are within about 1,000,007 square feet of connected building. We do have cooling towers, and I want to mention that the cooling towers are just there for the, oh my goodness, the wheels fell off of our system and I need to reduce heat from the system. And so if and when that's ever a problem, we do have cooling towers that we can use for supplemental cooling. We also have boiler plants that we kept online and connected to the tin, so that if our loop ever gets too cold in the winter, that we can heat that loop back up. Those cooling towers and boiler plants haven't run for some time now. And then we have 3 north and 3 south central loop pumps that we use to move fluid through our tin. Next slide, please. So this is the layout of our system. This gives you an idea of what the 144 acres on our campus looks like. The blue rectangular boxes that you see spread across our campus, for instance, from the very northwest corner of our campus south to the southern end of our campus are our drill fields, and we have 8 of those, though we just drilled a new one right here over the summer. That red and green lines, those red and green lines that you see, those are in fact central loop lines, and those lines connect our drill fields together with our resource to allow us to connect into buildings across campus. We do have several vaults that we use to control the system, or that's where we install our pumps that moves water throughout the system. And then we do have some smaller micro districts that recirculate loops so that water doesn't have to travel from the very south end of our campus north all the way through the 3 miles of pipe before it gets back to a building. So we do have some micro loops located across campus. Next slide, please. So what is a TIN? The basic component of a thermal energy network is what I refer to as a drill field. I'm sure there's a better term for that than what I came up with, but in short, we use conventional drilling rigs to drill a hole, an 8-inch or a 6-inch diameter hole into the ground. We drill that hole 600 feet into the earth, and we fill that hole with a thermally conductive grout. We then take a piece of pipe that's looped at the bottom, and it's an 1.25-inch diameter piece of pipe, and it's looped at the bottom, and we attach a weight to the bottom of the loop, and that pipe is pulled 600 feet into the ground. And then we take one side of that loop and move it over 25 feet, where we go down 600 feet into the ground again, come back the other side of the hole up to within 5 feet of the surface of the ground, and then we go back down, and so on and so forth. Those pipes that are installed in a drill field are then connected to larger pipes that bring that water resource into a pumping station. Next slide, please. And this is just a kind of a couple of pictures showing what the pipes look like that come from a drill field. So we have a drill field in the background that's beneath this green space, one of our academic quads. And this is also showing, and I have this picture because this just makes me giggle. This picture of the first drill field that we did back in 07, I swear that drilling rig was from World War II. It was old. The process was super messy. It was dirty. To today, where we drill with truck-mounted rigs that are they drill with air. And I'm not really sure how that works, but what I can say is it's much quicker, it's much cleaner, and it's much more economical. Next slide, please. So we drill those holes into the ground. We bring those pipes all together in a mechanical room in a building. And then we have pumps in that mechanical room that can move water through the drill field and can also deliver that water to our central loop. Our central loop was that line that I showed that extended from the south end of our campus to the north end of our campus. And this is actually a section of it that's 18 inches in diameter. A couple of things to note on this, TINs, or at least the one on our campus, the way you thermally fuse these pipes together, there's no electrical connect or no mechanical connections. Typically on a water line or a utility line, you'll have mega lugs and a cast iron fitting at each of these bends. And you'll notice that on this T, for instance, there is no fitting. The ends of these pipes are heated up and they're pushed together so they melt together. This is just showing a cast iron valve that we have. So we do have cast iron valves, but the rest of the pipe and all the fittings are thermally fused together. And this extends for a little over 2.5 miles to serve all of our campus. Next slide, please. So now that we have the drill fields and we have the central loop and we have this
Can't we just lost your audio?
my screen shut off, so I'm back. So then how does the system work? So we have this wonderful network of pipes that allow us to move heat from building to building. Our system works by what we have referred to as the least energy path. And I'm going to use an example. In a month or two, let's say end of October, early November, we have a classroom building. I'll use, for example, Dominguez Hall, where we have large lecture halls on the south side of the building. And when those lecture halls are full of 200 students, regardless of how cold it is outside, I can assure all on the call this morning that we will be removing heat from that lecture hall. The students that are in there are going to be generating heat, and we need to remove that heat. And so we use this magical box that's referred to as a heat pump to extract heat from that space and move that heat into a separate water loop inside the building. And that water loop connects a heat pump that serves the resident or the lecture hall to the offices on the north side of the building. So if we continue with that example, we extract heat from the classroom, the lecture hall, we move that heat into the building loop water, And then that heat is moved over to the north side of the building where we have offices. And those offices are going to be in shade regardless of the time of day. The sun's lower on the horizon, it's winter, and there's one person in an office. And so that office is most likely calling for heat. So the first least energy path in our 10 is simply to extract heat from one portion or one space within the building and move that heat to another space within the building that needs the heat. Once that building loop gets either too hot or too cold, we have the option with our central loop to run that water, that building loop water, through a heat exchanger. On one side of the heat exchanger, we have the building loop, and on the other side, we have the central loop. That heat exchanger allows us to either extract heat from the central loop and bring it into the building, or allows us to dump waste heat from the building into the central loop. Our next least energy path is then to take that heat and move it within the central loop to another building. And I'll use an example. We have a 800,000 gallon Olympic-sized swimming pool in our natatorium that's on the north end of campus. We heat that water 365 days a year. One of the things that we do with our central loop is right now in the summer, we're extracting heat from all of the buildings across campus. We can move that heat to provide preheat for the water that we put into the swimming pool. We can also use that excess heat to preheat domestic hot water. So that's our second least energy path. And so let's assume that it's middle of or end of summer, and even though we're dumping as much waste heat as we can't dump enough, and so there's excess waste heat in our central loop. That waste heat that's contained within the water inside the central loop is then sent down into the ground in one of those 8 or 9 drill fields. And as that heated water or that warm water moves through the drill field, the earth extracts heat from that water, so that when the water comes back to the surface, if we've designed our system correctly, and we have as many cooling loads as heating loads, that water comes back at the deep earth temperature. And so then it goes back to a building and the whole process starts again. That last bullet there is just to say that our loop fields, and not necessarily our loop fields, but our drill fields, we can use almost as a thermal battery. So we can store waste heat in that drill field as we enter the last part of summer, and then pull that heat out as we get into winter. So next slide, please. So one of the reasons that we decided many years ago, back in 2007, to install a thermal energy network, one of the many reasons was because thermal energy network is very, very cost effective. Heat pumps are very efficient. In fact, the coefficient of performance of our system at certain times of the year is in excess of 8. We had a study done by our local utility provider that analyzed the coefficient of performance of our system. And over the summer, it's as high as 6. And in some parts of the winter, it's as high as 8. The big picture numbers that I use is a traditional system consumes about 22 kilowatt hours of electricity per square foot per year, while a building served by heat pumps consumes less than half of that. That, of course, not only saves us money each year because we're buying fewer kilowatt hours from Xcel Energy, but it also greatly reduces our carbon footprint. And as Ashley's report states, it also saves us an enormous amount of processed water because we're not having to reject that heat to the air through a cooling tower. Next slide, please. This is just a graphic depiction of what the university would have spent. And I'm going to say would have because back in 2007, when we started installing our 10, our campus was at about 700,000 square feet. We are now just under 3 million square feet. And every new building or significant renovation on our campus has been connected into our 10 as we've continued to drill more fields and add more central loops. So those orange lines or bars on the graph would show what we would be spending on utilities had we installed traditional heating, ventilating, and air conditioning systems. Those blue lines are our actual spend. That's what we actually spent on electricity and gas over the summer. So you can see that we saved an enormous amount of money that we were then able to transfer to lower increases in our tuition and fees for our students. Next slide, please. And because we consume far less electricity than we would have had we installed a traditional heating, ventilating, and air conditioning system, we've also greatly reduced our carbon footprint. So that larger gray odd shape on the graph shows what our carbon load would have been had we installed traditional HVAC versus the orange hashed shape on the bottom of that graph shows our actual carbon footprint. So we've saved a bunch of carbon. Next slide, please. And so what's the financial investment? I can say that we benefited at this university from a leadership team, myself including, that was willing to move forward with a 10 a little over 15 years ago, and we weren't sure we knew everything about it. We kind of thought we knew how they worked, but we didn't 100% know how it worked. But we're very glad we did, because we found that, and I prefer to talk about payback rather than upfront cost, because I can guarantee that the sustainable long-term life cycle cost best option is most likely going to have the most expensive upfront cost. So our 10 is no exception. Our total cost of drill fields back when I did this calculation was at about $6.4 million. Our total cost, and that includes all the pumps and the central loop system, had us at about 20 million. And we were saving about $1.5 million, $1.6 million a year. So that alone would arrive at a payback of just over 12 years. So I think that's important, because the lion's share of resources in our system are large and small pieces of high density polyethylene. Those pipes will be in the ground forever and ever and ever. So those savings and our upfront costs we've paid back in 12 years, and that resource will be there forever. Next slide, please. Of course, there are challenges and there are lessons learned. Back in 2007, when we started this process, we found that the system that we could buy, the heat pumps that we were buying back in 2007, they didn't like really extreme changes in temperature between the central loop or the building loop and the interior temperature. They used to shut off if the delta T got too small, and the delta T being the difference in temperature of the loop water versus the temperature of a conditioned space within the building. That has since changed, and the new technology operates over a much broader delta T spectrum, so that's been a good thing. At the time, back in 2007, there wasn't many mechanical engineers that were familiar with how thermal energy networks worked, and so many consultants nowadays understand them, and I'm certain understand them far better than I do, and so that has also changed over the last 15 years. Again, back in 2007, when we decided to install high-density polyethylene pipe that's thermally fused together, there was no contractor in town that had any idea how to do that. Over the past 15 years, that technology has been used all over the United States, and I assume all over the world. And so there's 3 or 4 contractors in town here who do that thermally fused HDPE day in, day out, and they have no problem installing it. So that's certainly changed. And then the last consideration, and we still struggle with this a little bit, is the lack of construction and installation standards and testing procedures. I have just recently worked with a consultant that prepared a testing procedure for our drill fields and our central loop, and we think it's going to really help us before we let the contractor leave, to make sure that what they installed is going to last us for many years to come. So yes, those were challenges. We've certainly learned along the way. I'll say I don't know everything about the technology, but I know more today than I did yesterday. And we've come a long way in the last 15 years. Next slide, please. Okay, so what's next for Colorado Mesa University? For whatever reason, our system has gained a lot of attention over the last 2 years. In fact, the governor of the state of Colorado took interest in our system and was actually on campus 3 or 4 months ago He met with us, many of us, and was very interested in our system. And he was part of the Western Governors Association. In fact, at the time, I think he was chair, and he coined a phrase or a policy statement, I guess you'd say, that was called the heat beneath our feet. And our first project on his heat beneath our feet effort was our project. And that resulted in, I believe he helped us get spending authority of $9 million that I've been requesting for 3 or 4 years that will allow us to connect the remaining 800,000 square feet of existing campus buildings into our geo system. So that will allow us to drill additional drill fields and install additional central loop piping that will allow us to connect the rest of our campus into our thermal energy network. We've also learned over time that our heat loads, we need to better match our cooling loads with our heating loads. And so we know that we have opportunity to provide more water-to-water heat pumps to provide domestic hot water in our residence halls, in our university center, in our Maverick Center. A unique thing that we do on a very small scale that we'd like to do at a greater scale is we have heat exchangers that we connect to our irrigation system. We irrigate probably 90 acres of grass and landscape across campus. So we dump waste heat in the summer to that irrigation water before we sprinkle it on our grass. There's also opportunity for us to extract waste heat from sanitary sewer systems and potentially dump waste heat to a sanitary sewer system. So we're kicking the tires on that with our City of Grand Junction Public Works Department. And we think there's opportunity to help guide standards for IGSHPA, and that's the International Ground Source Heat Pump Association, long acronym, but we think there's need for greater codes and standards and greater understanding of how these thermal energy networks work. Next slide, and I hope I'm towards the end because I think I'm running out of time. I am. Jess, is it your turn?
Perfect. I will step back in. Thanks, Kent. And for those who don't know, Colorado Mesa University was the first to install the system of geothermal networks at the scale that they did, and they're the first to put it in the ground in 2008, as Kent mentioned. And this technology has inspired so many movements across the nation, from Massachusetts to New York, Illinois, etc. So thank you so much to Kent and his team for paving the way for this solution and coming up with all the solutions and additional challenges that we can all work on together. So I can talk to why this is important now. We know that water is only getting scarcer. The world is getting hotter, and we need to collect more data to quickly understand how TENS can help achieve multiple sustainable goals, like that of decarbonization, but also water conservation. Now is a really good time for me to mention some of the good reasons for all the momentum that's going on in the country. First, we have 7 states that have passed legislation that allow utilities to not only adopt, but also allows them to own and operate thermal energy networks. This includes 20 pilots that are being deployed across the country by various utilities, community groups, I'm sorry. And this is a chance for us to include more about water. So we're very focused on decarbonization, very focused on energy, but this is a crucial, pivotal moment for us to also include and be more comprehensive when it comes to water. Because Utility TENS is a pilot, data collection will be a part of those pilots, and so we will learn so much for the future neighborhood scale of decarbonization. In addition, we have systems that can take benefit of all the tax credits because of the Inflation Reduction Act. There are significant federal tax credit incentives for ground source heat pump installations within commercial buildings. Key benefits include the investment tax credit, or the ITC, which gives up to 30%, and an additional bonus for those that find a way to have those heat pumps made and manufactured in the US and address energy communities and their needs. It also includes new provisions for carrybacks and credit transfers. Next slide. And so, to wrap everything up, I'll leave you with some key recommendations for future data collection. This is only a sample of questions we would like to be asked, in addition to others that our counterparts will come up with. And so, what are the water savings achieved from replacing heating infrastructure, cooling towers, or both? Did any of the cooling towers remain after the geothermal system was installed, or was the cooling infrastructure completely replaced? And finally, how often are the cooling towers used when they remain in place, and what conditions merit that use? And Kent did mention a few of those, but with that, I want to thank you all for staying tuned and being a part of this conversation, and we can go to the next slide.
Thank you so much, Ashley. Thank you, Ken. And thank you to everybody in the chat. We have so many great questions. I hope we can get to all of them. And then just a reminder, what we can't get to today, we will send out in an email to everyone who has registered to attend. But Ken, there was a question about the cost of transitioning the campus to a thermal energy network, and I know you addressed that. I did want to ask as well, a follow-up to John's question, which is, do you have a sense of the projected ongoing repair and maintenance costs? And is there a significant increase or decrease compared to the past conventional system?
First part of that question was cost of, well, let me answer the last part because that's the part I recall. So is there any more maintenance or expense, let's say deferred maintenance that comes with heat pumps versus boilers and cooling towers? And I will say no. The real difference is there's a lot more rotating pieces in the field. So for instance, in a classroom building, I may have had a really large cooling tower on the roof, and I maybe had one or two thermific type or very efficient boilers. So there's fewer things for me to touch, but those things are much larger. The parts and pieces are much more expensive. That is replaced with 300 or 400, depending on the size of the building, heat pumps. And these heat pumps can be as small as a ton, 2 ton, but they're really, they're not super technology rich. There's compressors in there. It works the refrigeration cycle just like your refrigerator does, but it can both extract heat and dump heat to a space. So I don't think that there are more costs, either operational costs that come with owning or maintaining a thermal energy network. And by and large, the biggest part of our 10 is pieces of high density pipe that sit in the ground that no one knows it's even there. We never touch those. The valves, the pumps, all of that stuff. And even the pumps we use are run-of-the-mill pumps, and we always have spares. So if one dies, we go to the next one. So I don't think it's super maintenance intensive.
Ken, and correct me if I'm wrong, I want to make sure I say this correctly, but speaking of costs, you mentioned how the operating costs have gone down due to the energy efficiency savings from the geothermal system. And do I remember correctly that the tuition would be 2% higher today if it wasn't for installing the 10?
That's right. Yeah.
Okay.
Yeah. So what we did is we just looked at how much electricity we would have purchased today at our blended rate of 14 cents a kilowatt hour versus what we actually purchased. And we said, well, what is that net savings to our students? And that equated to a 2% reduction in what we would be charging for tuition today had we not installed the 10 that we have on campus. That's right.
That's amazing. That's real savings.
Yeah, it's awesome. Yeah.
Ken, while we're talking about the components, there are 2 questions from Noah that I am hoping you can speak to. And we'll start with the first one. Are the backup boilers on the system connected to piped gas, or are they fueled by tanked fuels?
So the boilers are connected to gas. We kept those just for worst case scenarios. So there's a heat exchanger between the boilers that would allow us to move heat from the boiler into the central loop. So let's just say that I make a mistake this winter and we build a new residence hall that we're moving forward with, and it's 104,000 square feet. And I don't have enough capacity in the existing 10. Well, in the winter, we're going to be pulling heat out of it like we always have. And let's say the loop gets too cold because I haven't drilled an additional drill field. We may have to turn that boiler on. I'm not sure we will, but maybe we do as a backup or a worst case scenario in case I have more connected load than I have capacity for. But then we would move forward in the future with, well, what do I need? Do I need an additional drill field, or is there some other way that I can deal with that additional heat resource? Where can I get the heat from? So they're just backups, but they are connected to gas.
Well, thank you. And then Noah's second question about components was, what kind of software manages the thermal exchange between buildings, the loop, and the bore field? And is it custom and unique to your system, or is this something that's commercially available and can be portable to other systems?
Well, I think it's commercially available. So we have Train Tracer Summit, and that is the direct digital controls that we have in the buildings. And that really tells the pumps in the building where to send the water. And then we have a larger, what we call our dashboard, that's based off of the hierarchy of the Tracer Summit system that is the brains that says where to turn pipes on and which pipes move water into the ground versus moving water through the central loop. So I think that's very common technology. I'm guessing there's some customization for our campus, but it's not anything different than any large campus would have. I would assume with your steam plant, I would assume it'd be very similar.
So interesting. Ashley, I have a question that is more about the adoption of TENS, and Kent, maybe you can speak to this too in your case. But Jessica had asked, are key decision makers in these situations amenable to TENS, or is it a concept that takes time to warm up to? And I'm wondering, Ashley, you might be able to speak to this a little bit from your work with the Thermal Energy Networks Coalition and with private developers of real estate.
Yeah, I would say that it varies. You can't even really say it's by state, it's really by coalition. And so being a coalition-based group, we defer and rely on nonprofits, municipalities, other utilities, regulators, labor, a whole host of stakeholders. And each coalition contains varying parts of those stakeholders. So not every coalition has utilities involved, not everyone has environmental justice involved, but they all have some variation. And I think each of their motives is different. And so it's hard for us to broadly stroke what the motives are for most folks, but a lot of it comes from some type of community need, or comes out of some community need, or some type of climate commitment that has been made. But what brings them together, I think, is this sense of wanting to make sure no one gets left behind. And that is really speaks to our the BDC's need and want to make sure that this transition is equitable. So even if a coalition doesn't have certain members involved, we ask those questions of, okay, who do you want involved? Who's not involved yet that you want involved? And are there any reason why you would want to have a separate table for other folks? Because we do believe everyone should be a part of the conversation and a part of the work, but maybe we work at different tables sometimes, like in kindergarten. Does that answer the question, Jess?
Yeah, it's funny how some of those early principles carry through to our work throughout our entire lives.
I could add some flavor to that too. So at least I have a very narrow focus, but in the higher ed world, I met with a very prestigious higher ed institution in Massachusetts. I won't name a name, but we talked yesterday. And I think what higher ed struggles with is many higher ed campuses are served by steam. And those steam boilers and all of that system are old, they're long in the tooth, and they're having to replace those. And so I think for an institution to take a step back and say, well, wait a second, we know we have to replace the infrastructure for our steam. Should we consider a different technology? Can we consider a TEN? I think it's important for higher ed to open their eyes to the possibilities, because once you replace that steam plant, that dinosaur is going to be there forever, because you're going to have so much sunken cost in replacing that thing. So I think for higher ed and for everybody, you need to look at it broadly.
Yeah, that's a great point, Kent. And that was something that we discovered and talked through with some of the universities that we were able to talk to, was the fact that some of the reasons of what drove them to attend specifically was the fact that they wanted to replace their failing steam system with something better. And I think Oberlin is a really good example of that, where they had the foresight to say, okay, we've made this climate commitment. We've also identified that like we are wasting tons of water that had nothing to do really with cooling, but it had more so to do with the failing steam system. And so their system is a little bit different than Colorado Mesa's because they use a 4-pipe system versus a 1-pipe system. But that is because, for those who don't know, it is very, very hard to transition old campuses off of steam. And so finding that sweet spot, and I think that also speaks to the beauty of a thermal energy network, is it can mix and mold to what the need is of the facility. And so it may not be, extremely efficient like the one CMU has with the ambient temperature loop, but it is extremely efficient when compared to a lot of the natural gas-based systems. So sorry, Jess, go ahead.
No, absolutely. I mean, so interesting. And actually that kind of brings us to another question from Ellie that I think is interesting. I want to hear from you both. So Ellie asks about recommendations of how to introduce new technologies for demonstration in a thermal energy network. And that specifically Microera Power is developing an innovative thermal energy storage solution as a way to reduce the size of the ground loop and looking for early adopters. And it's making me think about potential outreach to some of these universities and higher ed institutions. But Ashley, I was wondering if there might be something you can comment on in terms of the potential with legislation and policy. And then I'd love to hear from you too, Ken, after Ashley, about your thoughts on that.
Yeah, so I kind of see it from two different spots. And our fearless leader, Ania Carmago, she is our guru when it comes to legislative and regulatory elements of it. So I won't speak too much to that component, but I think from just looking at how the problems that folks are facing will result and present the need to be different when it comes to the solutions that come. When we think of ownership models, when we think of the utility world in general, how utilities work, whether they're private or publicly owned, whether they're dual fuel or they're just gas or electric, those things all play into how innovative we can be as a community when coming up with solutions. But I think it also presents a mass opportunity for us to think creatively and get innovative. It also allows for private non-utility investment. And so I always have to plug them because I love the work that they do, but EcoSmart Solution and Taurus Investments are two of the same company that work together to build sustainable communities. And so EcoSmart builds what they call a geogrid, which is them as private developers building public infrastructure for their master plan communities or their communities in general in order to provide a need. And so they never even look at gas infrastructure. They're constantly looking at ways to better make the grid more efficient and control peak load demand in both winter and summer. And so I'll let Kent kind of come in with
Sure.
his
So the
side.
question was, is there appetite for new and emerging technologies to be used to support or become part of a thermal energy network? Broadly, what I'll say is that my belief is that higher education has should lead by example, right? So I look back on 2007 and I say we really led by example by saying, we don't really certainly understand this well, but we have the smart folks in and around campus, and we can contract with even smarter folks to figure out how to make this happen. So Colorado Mesa University, and I assume many other institutions, higher ed and others in general, are interested in as technology advances, is it more cost effective, or does it save us long term? What does it look like? And would we consider it? Absolutely. We've considered, even we're told that you can drill vertically rather than straight down. We've even considered that, so we can have more length of drill field if it's on the hypotenuse of the triangle rather than on one of the legs of the triangle. So yeah, we're open to that for sure.
Yeah, and if I can also mention the first utility pilot that was completed back in June by Eversource in Framingham, Massachusetts. Is a good example of it's never been done before. They were looking at taking an entire community off of the gas system. And so if you can imagine, they're not starting at the main pipe, they're starting at different points at which it makes more sense to prune the system at once. And so identifying those communities involves a whole host of things, right? It took development of a criteria. It took time to talking to different communities. You have to get the consent of every single business or building owner, single family, commercial, et cetera, to get on board. And so I think innovation is going to come not just in the technology, but how we identify, deploy, and maintain and run these pilots that then will stop being pilots and they'll become actual capital projects that anyone, whether utility or community can, or campus for that matter, can do.
Yeah, absolutely. And it's one thing that we are looking at BDC too, and I'll share a link in the chat, is all of the different contexts in which thermal energy networks have been adopted for carbon management, for energy efficiency, and now hopefully for water savings too. So I just put a link in the chat of different sites. So feel free to take a look at that as well, because I think that could also spur some conversation about new technologies. Ken, I also had a question for you that is from Mansi. And is there a possibility that any energy is lost during the thermal exchange process? Have you computed how much is lost, if any? And then Ken or Ashley, can we talk about location? So are the TENS location specific?
Okay, so is there any energy lost? I'm certain there is. Where it's lost, I'm not sure. The majority of our system exists in the ground. Those pipes are all very tightly compacted with native material. Actually, we put sand around the pipes for bedding and haunching material, and then we compact the earth back on top of it. So I would say that any heat transfer that happens between our central loop and the earth, that energy, even though it's possibly within 5 feet of the surface of the earth, is probably not lost to the atmosphere. We probably still can extract some of that heat when we need it over the winter. But I'm sure there are ways for us to lose heat energy throughout the process. I don't know how much that is. I suspect it's not very much, but I don't know.
Yeah. What was the second question, Jess?
Are the TENS location specific?
Oh, yeah. No, they were, we have a database, which is an Excel sheet of all of the thermal energy networks that we are aware of that exist in the country, and in North America. And so, or actually it's global now. So I think we, highlighted those that we were able to get complete, both, water usage percentage, water usage in gallons, or water savings in gallons, and then their heating and cooling ton. There were a couple of other criteria that prevented some from being added, but for the most part, we relied on publicly available data to decide. So we didn't really have a specific geographic outside of just North America. So
One thing I could add, bigger context is, will TENS work throughout the US or throughout the world? What I would say is that yes, they will. But you have to be able to match the load. So for instance, we're cooling dominant in Colorado. So we have more heat than we can use. So we need to match the amount of heat that we pull out of a building with a resource that needs that amount of heat. I would assume that the TENS that were looked at in Canada and further north have the opposite problem. They need heat, and so they have to be able to match where they're pulling heat from with areas that need the heat. So that's the secret sauce to this whole thing.
yeah, and we can confirm that in places where ground source heat pumps may not be the best option, that air source heat pumps are the next best thing. So BDC is technology agnostic, of course. We want what's best for the communities and what's best going to get us to an accelerated decarb state, but we want to highlight those things that we know are scalable and efficient. And with thermal energy networks, it works very, very well to help with peak load management for the grid. And so being able, like Kent said, being able to move energy and not solely rely on the grid also provides an element of resiliency for a lot of communities and states. I live in Texas, so we can talk about that for a while, but the potential is boundless.
Thank you. And this is maybe a good moment to mention that we have a resource coming out on thermal energy networks and the grid, and we're at the hour. So for all registered attendees, we'll send out a link with our slides, with the recording, with questions that we didn't answer, as well as those we did, and resources to Ashley's point, and to the points Kent have made about thermal energy networks, where they are, resiliency, and other principles. I can't thank you enough, Ashley and Kent. Thank you for chatting today. I thank you to all of our attendees. Please stay in touch. Very excited to see more of your questions. And we will send out that link. If you have any other questions, feel free to contact me. My email address will be in the link that we send next week. Thanks, everyone. Have a great rest of your Thursday.
Bye, everyone.